Hello and welcome to Physics Review Videos. This is Unit 9, Sound and Light. Topic, what is sound? A quick review. When we're talking about sound waves, sound is going to act as a longitudinal wave. If you recall, there are two main types of waves we work with, longitudinal and transverse. In a longitudinal wave, the wave and the particle motion is parallel to one another. So a particle would vibrate or oscillate back and forth within the medium in the same orientation as the wave's motion. Or to put it a little bit more plainly, if the wave is moving to the right, the particles in the medium are shaking back and forth left and right, creating parallel motion. When this happens, the particles in the medium are either going to start bunching up in an area we call compression or spacing out in an area we call rarefaction. And when we view a wave in this fashion, to measure the wavelength, just as with the transverse wave, you look for where the wave repeats itself. So in this case, if I measure from compression to compression, that will be one complete wavelength. In the example now here on the bottom, we're talking about the motion of air molecules. When we're talking about sound, sound is actually the motion and the vibration of air molecules or a wave propagating through the medium of air. Now, the wave is moving here to the right. Again, we have compression and spacing out or rarefaction, and this is how a wave would work. Now, sound waves that we're going to be studying are going to be moving through the medium of the air, but keep in mind they can move through other mediums such as solids or liquids. Now, sound itself as a longitudinal wave is going to look like this. We're going to be dealing with air bunching up or spacing out. We have basically areas of high pressure and low pressure where we have high amounts of molecules that have bunched up or low amounts of particles that have spaced out. This allows us to graph those particles. So areas of compression, we can graph, and we're going to end up with crests where we have high pressure areas. Where the particles have spaced out, that's going to create an area of low pressure. Since a wave has this repeating motion, we're going to see the graph oscillate back and forth like a sine curve. Or another way we can think about it is graphing the pressure of a longitudinal sound wave creates an image similar to a transverse wave. Now, there's a couple of key reasons that we will do this. The main is that visually, it's a lot easier to represent and interpret an image like this, or the graph of the pressure. Even though we're doing that, please keep in mind that sound waves are always longitudinal. So even though they're being visibly represented in this format, they are a longitudinal wave. Now, something else to keep in mind is when we're talking about this, how you hear a frequency is called pitch. Now, if you recall, frequency and wavelength have an inverse relationship. I have a high frequency wave here. If I have a high frequency, I have a small wavelength. So the wavelengths are small in this portion. In a low frequency wave, I'm going to have a smaller frequency and thus a higher wavelength. How you hear a wave like this is going to be pitch. So for example, that will be a high frequency wave. So this top graph, if I were to hear this, the pitch I would hear would be something akin to this. This bottom image is a low frequency wave, or I could say a low pitch wave, and that's going to be more akin to this. So the lower the frequency, the bassier it's going to be. The higher the frequency, the more whistle-like the pitch. Another property of sound is volume. Now, when we're talking about volume, it's really represented, or you can think of it as viewed by the amplitude of a sound wave. If you recall from previously when we were talking about waves, amplitude is describing the energy within a wave. Volume is going to be akin to this. So if I have a very, very loud sound, I'm going to have a larger and larger amplitude. This doesn't determine or depend on frequency, and it doesn't determine or depend on wavelength. It only deals with the amount of energy in a wave. If you want to think about this in terms of how you operate, it would take a lot of energy to shout all day long. So if you were talking really loud for an extended period of time, you would get pretty tired because you're using a lot of energy. If you were to talk at a much quieter level, though, you would probably keep conversation going for a long amount of time. So the softer you talk, the less energy it takes. The louder you talk, the more energy it takes. That will be represented by the amplitude of the sound wave. Terms, pitch, again, is how you interpret frequency. And as before, frequency will be measured in hertz. Volume is going to be described by the amplitude of the sound wave. One last thing with this is dealing with human hearing. Since we're talking about how our ears interpret it, your ears are able to detect very certain types of sound waves. We can detect a range. So your ears can detect from 20 hertz to 20 kilohertz. If you recall, kilo stands for 1,000. So this is 20 to 20,000 hertz. That's the range of audible sound. Sound waves that exist beyond these frequencies are inaudible. And we have two types of inaudible waves. So if I were to go below a very low frequency, so if I have a low frequency or a low pitch sound, that's at the lower end. If I go below that, it's going to become an infrasonic sound. Below 20 hertz is a sound with such a low bassy sound that your ears actually cannot pick it up. That means they cannot interpret it and send the signal to your brain unless you don't hear it. Ultrasonic is at the other end. So if you have a very high-pitched sound that your ears will not be able to detect, we will be in the ultrasonic range. A very good example of this is a dog whistle. If you blow on a dog whistle, you actually will not hear the whistle sound, but a dog will. And the reason being is it's ultrasonic for human ears and out of our detectable range, but is not out of the detectable range for a dog.